Right. Thanks for giving your best effort, and I didn't expect these to be perfect. It's not going to be, but now I do want you to see what should have happened. Did good. Okay. So first of all, let's make sure we can use the word difference. When I walk by in the halls during class or my prep, and I see a student sitting out taking a test in the hallway, what would I probably infer? Yeah, they missed it. I don't know that, but doesn't that make sense? To infer to me means to make an educated guess without knowing everything. Because as I pointed out yesterday, we can't know everything. When they give the presidential approval ratings, I've never been asked once. So there's no way they ask everybody. And they don't have time to do that. In fact, think about it, if they did take time to ask every single person in the United States. Yes, by the time they get done, the answer would be different anyway. But there's no point in that. It costs too much on that. They don't need to do that. So even though a parameter describes the population, the true percent of people that approve of President Trump's handling, we'll never know that. We will never know that. Instead, we take a sample, and when they say 41%, that's actually called statistics. Now, do we hope that this is really close to that? Yeah. If you do a good job, and how many different kinds of samples do we know how to take? Simple random sample, stratified, cluster, systematic, multi-stage. I know it's been a while, we'll come back to that. We know how to take lots of kinds of samples, and they all work, but that's what they do. They take the samples, and the numbers they get, they hope that they're pretty close to those. Then I asked you to build a sampling distribution, and I didn't even tell you what it is. All I wanted you to do was find every single sample there is. So I gave you a couple. So again, here's the thing. It's a weird population. If one person is 1 foot tall, one person's 2 foot tall, one person's 3 feet tall. So remember the name for this kind of distribution right there? Uniform. Yeah, that's called uniform. So that everybody's equally likely. That everybody in that population has a chance of 1/6 of being picked. But you gotta pretend with me. Gosh, I don't have time to talk to 6 people. I know we do. But I gotta show you how small populations work. I mean, would you rather start with a population of 30,000? We can't start with that. We gotta start with really small populations. And if you understand how really small populations work, then you can understand how 300 million people in the United States work. So instead of talking to all 6 people, if I wanna know the average height, and by the way, the average height of this population is, that's it right there, it's symmetric, it's gotta be 3.5. So we know, in fact, here's how we're gonna write this then. The population mean height is 3.5. What kind of number is this? What do you call it? It's called a parameter. It describes the population. They even use alliteration P for both. This is a parameter. It describes the population. Could we also find the standard deviation of the population? We could do that. I don't know what it is, but we could find that. You write this. What I asked you to do instead was take a bunch of samples and start collecting the data from those. And I gave you a couple. So if for some reason my sample had only included those 2 people, well, I got one person's 1 foot tall, one's 2 feet tall, the average 1.5. Wouldn't I go around thinking, if that's the only information I had, that the average height of the population is 1.5? It's not a very good sample, is it? Because weirdly, I just happened to get the 2 shortest people in the whole group. That's not likely to happen, does it? But it could. If instead, my sample happened to be those 2 people, well then I take the average and I got 2. Then I start to go around thinking, I think the average height of this population is 2. I know it seems silly to take samples out of a group that's only 6. We gotta start somewhere. Keep going. And I don't know what kind of number you came up with. If you just, and did you know when you were done? We did talk about 6 choose 2 happens to be 15. So when you get to 15 of them, you're done. You just gotta put them all together. So I got a couple of groups, where am I here? Yeah, I had a couple of groups that hit at 2.5. Only 2 of them actually. I had a couple of groups that hit at 3. We don't have yours to look at, I'm sorry, but I wanted to get it in from you. The most popular value, weirdly enough, that's not weird, the most popular value was 3.5. So just as an example, if I got, persons 3 and 4, they have an average of 3.5. 2 and 5, they have an average of 3.5, and 1 and 6. So there's 3 different groups that can actually give you an average of 3.5, and that's the right one, isn't it? That's the right one, finally. I got a couple of 4s. Yeah, if yours isn't perfect, that's okay, because you haven't done this before. I got a couple of 4.5, 4.5, so I got a 5, I got a 5.5. Do you know where this one came from? Well, it had to be those two people, didn't it? If those happen to be my samples. That's 15 samples. That is, right there, that's a sampling distribution. If this is really important, at some point I need you to be able to say, what the heck is that? What is a sampling distribution? That's one right there. That's a population. That's a sampling distribution. What is it? Well, even if you didn't know what we were talking about when we walked in, and they just asked you, hey, what do you call that kind of graph? You'd call it, it's a histogram, that's fine. If somebody else had said PDF, that's fine too, because doesn't it have the X values? We're used to seeing PDFs like this, where you got the X values, and you got the probability X is down below. It's the same thing, isn't it? And why are the X values here? They're 1, 2, 3, 4, 5, 6. And every single probability is 1/6. What are the X values here? 1.5, 2, 2.5, 3, and you could list the probabilities, couldn't you? So if you want to call it a histogram, that's fine. If you want to call it a PDF, that's fine too. And then it got a little bit more complicated. Then we said, well, if I want some better information, why don't I take a larger sample size? By the way, that's one of the cure-alls in stats. If you want more information, take a bigger sample. Now we're going to take a look at samples of size 3. So one possible sample is the people 1, 2, and 3. And weirdly enough, the average of them is 2. I just kept going, and this was a little bit harder. I don't know if I can show you my chicken scratch. Admittedly, I got lost a couple of times. I tried to do what you guys do, which is do this while I was watching TV, and it wasn't a good idea. I had to write them all out to make sure I wasn't missing anything. That's what it's messy, I know. That's what it looks like. I even had to check myself to make sure, oh yeah, that's right, there's 20 of those, aren't there? Okay? Yeah, there's 15 on the top one, there's only 20, there's 21, 20 of them in here. And I actually had to write them out to make sure I wasn't leaving something out, to make sure I wasn't duplicating things like that. So that's what that sampling distribution is. Still, what I'd like to have you do, now you've seen, wow, 2 sampling distributions in your whole life. Write them down, what are they? What is a sampling distribution? If you're wrong, it's okay, it doesn't matter. I get the fact that it's a histogram. I know it's a PDF showing what, that's important. All of them? Aggressively wrote this. Yeah, there's 2 different samples. Pretty good. You got 2 shredded feet.
What is happening? What is better?
Yep. I'll use it.
Hey.
Hi, you feeling better?
Yeah, it was good.
I
think my dad and I tried to put nutmeg in a pie.
Are those two good one?
Isn't it weird? Well, I see 60 left, I don't like this single time.
My dad would make like chocolate mud cake,
Yeah, how did that?
like an Oreo crust.
I like
Yeah, no,
Oh, I seen that one, it was so funny, he was like, he smiled the whole time, he was like not acting like, yeah, I was like, oh. I know.
I like that they have the craziest teacher, one of the shooters,
Who was that?
Jackson.
That's what I thought. I thought it was Rome. No, I didn't know.
Jackson.
You get kicked out?
I don't know how it was. Just get on the
Oh.
I don't know. I got everything done.
I didn't. Can I steal yours?
I mean, yeah, I can read it. I literally did it all last night. I was like watching it. It's like, it literally like, I think I had like 3 pages of that big packet down.
I don't have a cat like, that she gave us when she was 5.
I have that old chunk.
So I guess I'm asking you to define something that I've never told you before. That's fine. Gave you a couple examples. This isn't bad. The key I like, it shows all of the possibilities of the given sample. It shows every possible sample you could ever take. Do you understand why I started with a small population?
Yeah.
Would you like to, how about even a population size 100 and list every single sample you could take? So it would take forever. This took me 10 minutes as it was. I don't know how long it took you to list them all. That's exactly it. This is pretty good. A sampling distribution is a histogram, that's true, that shows every single sample you could ever take and how likely they are. How's that? Every single sample you could ever take, they're all there, and it shows which ones are most likely, which ones are least likely. Do you remember why were you even taking a sample in the first place? What were we trying to find out about this population? The average height. I want to know the average height. I want to know the average amount of debt that college students have when they graduate. I want to know the average price people are paying for a car. I want to know the average commute time. We want to know average all over the place. I want to know the average height, okay? Average height is actually 3.5. Some of our sampling distributions, are better than others. And there's some things that are the same. So the next thing I'd like you to do, I don't know what you said on your papers. I guess they're here. How are these the same? There's 3 of them.
You're supposed to be here.
Technically, could you call that a sampling distribution of size 1? If you only take a sample of size 1, nobody ever does that. How are these the same, and how are they different? Particularly now, if I put all the other X's back up in there. That's what we need to know. How are they the same, and how are they different? How are these 3 the same? How are they different?
Yeah. But the sample size of 3 has more precise data because you're taking a larger portion to...
Good. Okay, that's how they're the same.
Bigger sample you take, the higher chance you have to get closer to.
Yeah.
Differences. The second one is more precise.
Are you just listing what's the same? Something else.
Second one, like the size 3.
So is this a similarity or a difference? Because this is, so they're all symmetric.
One thing is going to be 3.5 or...
I tried. So you can't do anything.
We got like 5 already.
Okay.
Your ass is so weird.
I don't expect it to be quick.
the standard deviation.
Now you see it. You can still get bad samples. Okay. Hey, one way to look at this, aren't the worst samples in the middle one?
He goes, oh, it's just using He said like something.
So spread.
Either way, it makes sense.
That's the word I was looking for.
Me too.
You know what? No.
There are also metric for which is not a shape. Or a shape and symmetry. Obviously for the opposite, but I think
You don't want to have high.
Do you want to come down here?
I'll just say symmetric, but shape is still different.
Because you want more spread on the
Well, they're
jelly.
both
You don't
symmetric.
want less, you don't want spread on the jelly.
Yeah.
Shape's different.
Alright guys, there's 5 or 6 really important things you guys all said, which are good. To clean it up together, aren't they all symmetric? Okay. Be careful, that doesn't always have to be the case. I gave you a symmetric one to start with. If the population happens to be symmetric, then what do you call these things? The sampling distributions are symmetric too. In fact, we're going to find out later on, if the original population happened to be normally distributed, then these are normally distributed too. Be careful, these are not normal. They are symmetric, but they're not normal. Most of you pointed out, hey, they have the same mean. That is true. In fact, we're going to have to write that a certain way. Remember Goldilocks and the 3 bears? The little girl goes around, she's trying to sleep in beds, and you have pour, this one's too hot, this one's too soft. Well, watch what happens. Hey, this sample mean is too low. This sample mean is some of the sample means are just right. And in fact, on average, the sample mean is just right. We have a way of saying that. Instead of the Goldilocks, and when I kiddingly refer to Goldilocks, I'm like, oh, that's right. Some of them are too low, some of them are too high. On average, I guarantee you that not only are some of them just right, but on average, the sample mean is just right. That means, well, I'm trying to use the words, but the sample mean we call unbiased. Now that word gets used in the media for different things. To us, unbiased means sometimes it's too low, sometimes it's too high, but on average, it's just right. If you think you're unbiased in whatever regard, do you get it right every single time? Probably not. And that's what unbiased means. On average, it gives exactly the right answer. Don't expect it to be right every single time. See if this makes sense. Did you know that the average of the averages is the average? Let me say this in a better way. The mean of the, what are these? Sample means, no, okay, you guys do get it. Yeah, the mean of the sample means is the population. The mean of all the sample means is the population mean. Hey, we just said the same thing in a different way. Now I'm going to say it a third way. How do you say sample mean? That's how you say sample mean. How do you say mean of all the sample means? Equals what? Oh, the mean of all the sample means is the population mean. This thing is what kind of number? What do you call it? It's called a parameter. These are all statistics, but if you do things overall, the mean of all your statistics is your parameter. Now again, some are better than others. Well, we're not saying that every single one's right, but we are saying on average it is exactly what it's supposed to do. And I said, you noticed that. Nobody wrote it this way, I didn't expect you to. Most of you said, hey, they all have a mean of 3.5. Beautiful, you're right. So we looked at shape, looked at how the mean compares, and then some of you started saying things about, got a word for this? Spread, variance, standard deviation, spread outness. Yeah, you're right. In fact, I saw a couple that wrote a statement, as the sample size goes up, the spread outness goes down, doesn't it? I don't know, can you tell that this is less spread out than that is? On purpose, I tried to leave the numbers lined up so you could see this. On purpose, I did that. And that's true. What's the biggest sample size we could ever take in this instance? Well, 6, yeah. Now, nobody goes and talks to the whole population, that'd be silly. And what would that sampling distribution look like? Yeah, there'd be 1x right here, it'd be perfect. The standard deviation would be 0. So that's true. As the sample size goes up, the spread outness of the what's? What are these things called? Sampling distributions. As the sample size goes up, the standard deviation, the spread of the sampling distributions goes down. That's a lot of stuff, and that's really important. Why don't you take a lap and come back?